So this guy comes into the lab, really excited. They've just measured the first image of a black hole. And my immediate response was, bullshit. Let's start with the obvious. We can't resolve stars, local stars, as anything other than point sources, even with our most powerful telescopes like Hubble. Black holes are a damn sight smaller than stars. Seriously, if we were to turn the sun into a black hole, the event horizon would fit within most cities. Then he tells me, but it's not even in our galaxy. At which point I say, now I know you're really talking crap. Local stars are just a few light years away, and we can't resolve those as anything than point sources. Galaxies are millions to hundreds of millions of light years away. You definitely won't be able to resolve stars there as anything other than point sources, and you can't make an image of one point. Then he mentioned something interesting, that it was in a galaxy called M87, at which point I kind of quietly chuckled. I've actually seen M87, this galaxy, with the naked eye, well, through a telescope. And even with a good telescope under a dark sky, you're not really going to see anything other than an oval smudge of light. However, M87 is famous for one thing. It's got this large jet coming out the middle of it, which has been thought to be due to a massive black hole. But to actually see that jet, you need a really long exposure taken with a really impressive telescope. See, M87 is close in intergalactic terms, but still a very, very long way away, to the point where this is the best resolution image that Hubble got of it. And you can barely see any stars there. Well, other than the ones in the foreground, the ones in our own galaxy. All you get is this general featureless glow, which is caused by billions of distant stars. So what the hell is going on here? What did these boys image? I mean, they don't look like they're making it up to me. Well, you've got to understand what it is that telescopes actually do, and to a degree, how they do it. You see, what telescopes do is they allow you to see faint objects and small objects. The ability to see small objects is called resolution, and it depends on the diameter of your mirror or lens. Now, if you've got a bright but small object like a planet, then you don't really need a big telescope to get lots of photons. You need it for the resolution. Now, in terms of resolution, the optical limit is basically dependent on the diameter, the baseline of the mirror. And it turns out that once you get up to about 12 inches or 30 centimeters, it really doesn't help you to get a bigger telescope than that for resolution, because you are always limited by the atmosphere. I mean, sure, a bigger telescope will help you get more photons and see fainter objects, but it won't help you see smaller objects. But what if we were on the moon? What if you weren't limited by the atmosphere? Well, sure, then the bigger the baseline of the telescope, the better the resolution. But it turns out that because of the way the optics work, you don't need the whole mirror there. Just a few parts of it will work fine in mostly keeping the resolution. Now, in a telescope like this, you can just put your eye to the eyepiece and it would work fine, because you're keeping all of the wavefront data. But building a telescope like this is really impractical. So there's this trick that rather than building one giant telescope, you get lots of little telescopes, and then, because this turns out to be important for the optics, you've got to record the same wavefronts. And seeing as that light arrives at the telescopes at different times, you've got to hook up delays between when they actually record their data. And from that, boom, it turns out you can get the resolution of the large effective diameter telescope. Now, that might sound nightmarishly complicated, and to a degree, it is, but it's a damn sight easier than building one giant telescope. So a typical radio interferometer looks like this. Interferometer is just one of these devices that uses this partial effective mirror trick to get better resolution. But they're not limited to single-site machines like this. You can actually spread your radio telescopes all over the surface of the planet and have an effective radio telescope diameter of the entire planet. Now, for a variety of reasons, it turns out this is much easier to do with long wavelengths of light, things like microwaves and radio waves, and much harder to do as the wavelength of light gets shorter. The practical upshot is the world's biggest visible interferometers have a baseline of about 1/3 of a kilometre or so. Now it turns out with a baseline like that, you can just about get an image of a star as a non-point source. So how are you going to get an image of a black hole in a distant galaxy? Especially when this was the best that Hubble could do. Well, you need a really big interferometer, one of these ones that works on a planet-wide scale. And because of that, you need to work at a much longer wavelength. So these guys were working at a wavelength of about 1 millimeter. So that's the visible spectrum there. It's about a micron. That's 1,000th of a millimeter. And now we can zoom out to 1 millimeter, which is about the thickness of a dime. And just for reference here, the microwaves that you use to cook with in the microwave oven have a wavelength of about 12 centimeters. That's about 12 dimes per end to end. And obviously, once you get an effective baseline, an effective diameter for your telescope the size of the Earth, now we're talking angular resolution. Cool. So how angularly big is this black hole? Well, let's just take the moon as a benchmark here. If you get a circle and chop it up into 360 portions, each one of those is a degree. So the moon and the sun both appear in the sky as about half a degree in size. Now, if you take one of those degrees and chop it up into 60, each one of those is an arc minute. And Jupiter from the Earth appears as about 1 arc minute in size. So if I get a camcorder and zoom right in on the moon and right in on the Jovian system, the Jupiter system, what I find is Jupiter and all of its moons are about the same angular size as the moon. So Jupiter's diameter is about an arc minute, comparable to a large crater on the moon. And just so we've got this all in perspective, the entire M87 galaxy, not just the bright core, the whole thing is about 7 arc minutes in size. And each arc minute, you'll be happy to know, is cut up into 60 arc seconds. An arc second is pretty much the best resolution that you can hope to get from a terrestrial-based telescope, like this one that I was talking about earlier. It's also about the angular size of the 4 big moons of Jupiter. Now, those moons are about the same size as our moon, but obviously a long way away. So that's 1 arc second in size. Or you could resolve about 60 features across the disk of Jupiter with a good telescope on a good night. So how big is this black hole in comparison? Angularly, it's about 1,000,000 times smaller than an arc second. It's not measured in arc seconds, but millionths of an arc second, micro arc seconds. And just for reference here, Hubble's best resolution was about 1/20th of an arc second. So this is still about 1,000,000 times smaller than Hubble could resolve. That being said, this is still not enough to resolve a black hole, because in reality, you can never see a black hole. They're about the size of an atomic nuclei. They're a singularity. So if you were to magnify the air that you're breathing by a factor of about 1 billion, you would see something like this. Well, kinda. The details are explained in Life in the Ball Pit. Yeah, I think that's air you're breathing. So you get down to the atoms, and then you have to magnify those also by a factor of 1 million, and you'll get down to the size of the atomic nuclei. That's about the size of a black hole. You can never see them. However, black holes have this border around them, from which the gravity is so strong that the light can't escape. It's called the event horizon. It's essentially the point of no return. Now, event horizons for black holes of stellar-type masses are typically tinier, a few kilometers, that sort of thing. However, the black hole in M87 is just a tiny bit bigger. Now, technically, it's exactly the same size, of course. They're all singularities, but its mass is much bigger. It weighs as much as about 1 billion suns packed into this thing, which is really quite impressive. It's about 1% of the entire mass of the galaxy. It also means that the event horizon is quite big. And when I say quite big, no, not just a few kilometers. No, that's nothing. Not bigger than the Earth. That's tiny. Or bigger than the Sun. Also insignificant. Not bigger than the Earth-Sun orbit. Again, that's nothing. If you were to zoom out such that you could see the entire solar system, the event horizon of this black hole is about 4 times the diameter of our entire solar system. Now, this video is going to be about 10 minutes in length, that sort of thing. So in that time, light that was leaving the sun will have just about arrived at Earth. In about 4 hours, the light from the sun reaches the edge of our solar system. So it takes about 8 hours for light to cross our entire solar system. Or it would take about a day and a half for light traveling the equal distance from event horizon to event horizon across this black hole. But that's still not what you're looking at here. You see, the innermost stable orbit you can get around a black hole is about 3 times the diameter of the black hole, of the event horizon. And that's the thing that you're actually looking at here. That's what's emitting the light, because the stuff in orbit there is moving almost at the speed of light, so it's really hot. Well, let's put this in a human perspective. The most distant man-made object is Voyager 1, and it's about 20 billion kilometers away. So if we were at the center, Voyager 1, the most distant man-made object, would have only just reached the event horizon there. That's how big this object is. So not only would light take over a week to go just from one side of this structure to the other, assuming there wasn't a black hole in the middle, of course, it then takes another 55 million years to reach us. That is, when these photons were leaving the black hole, when they first started their journey, the dinosaurs had only just died out. But it's the massive size of this thing which is why you have a chance of seeing it. Well, that plus the thing that we're not looking in visible light, but light with a wavelength of about 1 millimeter. These are not real colors. And we're using an interferometer with a baseline the size of the planet. And so if that inspired you to look to the heavens and actually see some of this yourself with the naked eye, for the night is dark and full of wonders. The moon and the planets are always fantastic, even from small telescopes from cities. And in a dark sky, the sky is full of galaxies and nebula, and some beautiful binary stars. So if you want to see some of those for yourself, I'll leave a link at the end of this video about which telescope would be right for you. Because believe it or not, bigger isn't always better. Trust me, this thing weighs a ton. Sure, it can do some fairly impressive stuff like a time-lapse of an exploding star, a supernova, or a time-lapse of an entire rotation of Jupiter from the spinning surface of the Earth. Or I'll leave some Amazon affiliate links to telescopes below that I would recommend for different users in different conditions. So if you enjoyed that, give this video a thumbs up and hit the like and subscribe button. And if you want more behind the scenes footage or just general blogs, you can see my other channel, Voice of Thunder. And if you really enjoyed this and want to support this channel directly, you can do it through Patreon. And I'll leave the links below.